Hi folks, welcome to the Math 621B Chapter 6 Concept Roundup. As always, there are downloadable notes in the video description below, as well as a Chapter 6 assignment that you can try on your own, and we'll put solutions to that assignment at the end of this video. The big ideas in Chapter 6 have to do with using trigonometric identities, and basically what we're doing is finding alternate ways of writing some facts about trigonometric expressions. So you can read here what the different topics are. This is not an exhaustive list of everything that's in Chapter 6, but we're trying to hit the highlights. So the first idea is non-permissible values. Numbers that can't go into an expression because they make the expression undefined. So all you need to do is consider any values that make any part of the expression undefined, or that make the bottom of a fraction 0, which in turn would make the whole expression undefined. So here we want to find the non-permissible values of cotangent x and sine x over sine x minus 1. So we're going to ask ourselves, where is cotangent undefined? And from our work in Chapter 4, we'll know that cotangent is going to be undefined at these spots on the unit circle. Okay? Because cotangent is cosine over sine. Wherever sine is 0, we're going to have cotangent undefined. So that's 0 and pi if we were talking about the first revolution. If we were talking about solving it for all x, finding all those non-permissible values, we just look for that first one, and because it's a tangent, we add on pi n. The other thing that we watch out for is values that make the bottom 0. So making cotangent 0 is no problem. You can have a 0 on top. But having the bottom, or sine x minus 1, be 0, that's trouble. So let's find out what values do that. If sine x minus 1 is 0, then sine x is 1. And the only place that happens is at pi over 2. So in total, our non-permissible values, we're saying that x cannot be 0, pi over 2, or pi in the first revolution. Or if we were to say it for all x, we'd say that x cannot be 0 plus pi n, or you could just write that as pi n. And it also cannot be pi over 2, and that solution, or non-permissible value, recurs every 2 pi units. The most important thing is that you can do it in the first revolution. Okay, so after we deal with non-permissible values, we have all these angle, sum, and difference identities. And again, there's a handout here that you can download and you could print off, and it's got all these formulas. They're also in your textbook. And all we do with them is we try and use them to simplify some expressions. So here we've got cos 17, cos 43 minus sine 17, sine 43. It would be great if we could make that into a more straightforward expression. So I have to look for that type of formula on my angle, sum, and difference formulas. So it was cos minus sine. Where's cos minus sine? Right here. It's angle sum for cosine. Which means I can rewrite this as the cosine of 17 degrees plus 43 degrees, which is the cosine of 60. And we know that the cosine of 60 is a half. Similarly, we could work it out for this one here. So the format of this one is sine cos plus cos sine. Let's find that on the angle, sum, and difference ones. Sine cos plus cos sine. Oh, that's the very first one. That's angle sum for sine. So I should be able to rewrite this as sine of 2 pi over 5 plus pi over 10. Get a common denominator, and that's 5 pi over 10, or pi over 2. Now it's easier for us to evaluate. Sine of pi over 2. Turns out that that big long expression we started with was just a pretentious way of saying the number 1. The other thing that the angle, sum, and difference formulas do is they allow us to find some values of sine and cosine and tangent that we couldn't find before. So before we only knew what to do with multiples of 0, 30, 45, 60, and 90. Right here, we're asked to find the sine of 75. Now you ask yourself, can I express 75 as the sum of some angles I know something about? So if you wanted to, you could say, well, this is 50 plus 25. But that's not helpful. We don't know anything about the sign of 50 or 25. If we split it up, however, as 30 and 45, that would be good. Okay, so now we can go and use the angle sum formula. For sine, it was sine cos plus cos sine. So sine of 30 times the cos of 45 plus the cos of 30 times the sine of 45. And if you want, the Khan Academy has great proofs, walkthroughs of the proofs for each of these trigonometric sum formulas. Okay, let's work it through. Sine 30 is 1 over root 2. Cos 45 is root 2 over 2. Cos 30 is root 3 over 2. And sine 45 is root 2 over 2. Giving us a grand total of root 2 plus root 6 all over 4. Cos 165. We're going to do something very similar here. But we can't express it as one of the ones or two of the ones in our first quadrant added together. We have to think about how we can use those as reference angles. So 165, there's a whole bunch of ways that you can write it. But this way is probably the most straightforward in terms of us trying to find this value. Now you might say, well, cos 120, we don't have that in our table. Yeah, but it's the same reference angle as a 60. Okay. So we should be able to work this out. This is a cosine sum formula. So it's going to be this over here, cos A, cos B, minus sine A, sine B. Let's set it up. Cos 120, cos 45, minus sine 120, sine 45. Cos of 120 is negative a half, okay, because the cos of 60 would have been a half, but we're over here in quadrant 2, so we're negative. Cos of 45 is root 2 over 2. Minus sine of 120, that's root 3 over 2. It's positive because it's in quadrant 2. And sine of 45 is root 2 over 2. Put them all together, and we get negative root 2 minus root 6 over 4. Moving on, using some of those formulas a little more to write as a single trig function. So right over here we have 10 sine x cos x. When you see these, you want to go to your formulas and say, is there anything that looks kind of like that? So we had 10 sine x cos x. Right over here, there's a formula for 2 sine A cos A. It equals the sine of 2A. That's really similar to what we have. In fact, let's just build that idea of a 2 sine x cos x. And 10 sine x cos x is just 5 of these 2 sine x cos x's. So really I just factored 5 out of that. From the formula, we know that 2 sine x cos x is the same as sine of 2x. So this whole thing becomes 5 sine 2x. I can't multiply that 5 inside because the 2 has to do with the angle. Okay, same thing over here. We've got cos 2x, and we want to express this thing as a single trigonometric function. Cos 2x has a bunch of different formulas. Okay, so looking over here, 3 different ones. Now, if you think about the top on that function that we just had, we had cos 2x minus sine squared x. If we want a single function, plus sine squared x. If we want a single function, we probably want to get rid of that sine squared. So which one of these 3 are we going to choose? You can actually choose either one, or any of the 3 rather, and use your Pythagorean identities. But the fastest one to choose is going to be this one. Because look, if we put it up top, we'll have cos squared of x minus sine squared of x plus sine squared of x. Hello, those are gone. So we do have to think a little bit creatively about what's going to be most efficient for us. Let's work this through. So we said cos 2x here can be written as cos squared x minus sine squared x, straight from the formula sheet, all over cos x. The sine squareds are gone, so we have cos squared over cos x, and we can divide out. So that whole messy expression we started with just means the cosine of x. We're going to work a little more with identities. We had those double angle formulas, angle sum and difference formulas. Here are some basic definitions. Cosecant is 1 over sine, secant is 1 over cosine, and so on. We also have these Pythagorean identities. And this first one in green, it comes from the unit circle, essentially. The next one is just what you'd get if you divided that whole initial one by cosine squared, rather. And the last one is if you divide it by sine squared. Okay, so they're all true and they're all given. And what we do is we use them in order to prove other trigonometric facts or to write things in a simplified form. And first off, we'll just get some practice doing some of the algebra around trigonometric functions, and then we'll do some proofs. Okay, so here's the first one. Sine plus cos all squared. Is there an easier way to write it? Let's find out. So it's saying expand, and we should assume that we want to simplify as well. Okay, if I work these out, I'll get sine times sine is sine squared theta. I'll get a sine cos and another sine cos, so that's 2 sine theta cos theta, and plus cos squared theta. Now, are there any trigonometric facts we can use? Here's a sine squared plus a cos squared. Together, those make 1. So this whole thing really just means 1 plus 2 sine theta cos theta. If you wanted to go even further with it, you might recognize this as the same as sine 2 theta. That was your double angle formula for sine. So in the end, we could write that whole expression we started with as 1 plus sine of 2 theta. Let's try working with some fractions. So one thing you can do to reduce fractions is to factor them. And in fact, it's your best plan. So up top, we've got a short trinomial on this one. I'm looking for numbers that add to 3 and multiply to 2. So I could factor this as cos theta plus 2, cos theta plus 1. Down below, there's a common factor of sine theta. It's only once they're factored that we can start to divide elements out. So you can see these are identical on top and bottom, and the whole expression could read cos theta plus 2 over sine theta. Okay. And this is discounting any of the restrictions that we may have glossed over. We don't worry typically about the non-permissible values. We just go and simplify, and we say it's true for all values where the original function was defined. Okay, expressing as a single fraction. That typically means find a common denominator. So over here we have 1 over 1 plus sine plus 1 over 1 minus sine. If I want a common denominator, I'm going to have to, I think I'm going to have to rewrite the whole thing. 1 over 1 plus sine theta. And give myself a little more room. The common denominator would just be both of those denominators multiplied together. So 1 plus sine theta times 1 minus sine theta. That means missing from this one is 1 minus sine theta. So I'll times the top and bottom by 1 minus sine theta. Over here, what's missing is 1 plus sine theta. Okay, let's see what we get. I'd get 1 minus sine theta all over 1 minus sine squared plus 1 plus sine theta all over 1 minus sine squared. Now we have a common denominator, and we can work. Okay, so put them together. That's 1 minus sine theta plus 1 plus sine theta all over 1 minus sine squared theta. That's a 2 on top. And you might notice from Pythagorean theorem, or the Pythagorean identity, if this is true, this could be rearranged. We could say that cos theta is 1 minus sine squared theta. So that 1 minus sine squared theta could be written just as easily as cos squared theta. Okay, so that could be our final answer. Or if you were feeling really fancy, you could call this 2 secant squared theta. Now in the next one, it asks us to express it as a single fraction. It doesn't look like a fraction at all. But we could write each of these expressions as fractions. So cotangent is cosine over sine. Tangent is sine over cosine. If we wanted to put them as a single fraction, we'll need a common denominator. So the common denominator is going to be sine times cosine, which means I need to multiply this first one by cos over cos, and this second one by sine over sine. That gives us our common denominator of sine times cos. And on top, we'd have cos squared plus sine squared, or 1 over sine theta cos theta. If you didn't want it in fractional form, you could write this as secant cosecant, but this is fine. Okay, and the reason we have that 1 is because cos squared plus sine squared is 1. Let's try this next one. We want to get a common denominator here, so we have cos theta over sine theta plus 1 plus sine theta. That's really over 1. To get a common denominator, we'll have to multiply by sine theta plus 1. Okay, let's see what that gives us. It'll give us cos theta plus sine squared theta plus sine theta all over sine theta plus 1. And there's really not a whole lot we can do beyond that to that expression. Okay, same sort of idea here. We want to put these together. If we've got a whole bunch of different looking terms, a good plan is to bring to sine or cosine. All of our ratios can be expressed just as sine and cosine. So here, if we have sine x plus cos x times cotangent, so that's cos x over sine x. We could write it this way. Okay, now to put them together, we're going to need a common denominator of sine. So we'll get sine squared x plus cos squared x all over sine x. Oh wow, that's a sine squared plus a cos squared? That's another way of saying 1. So we could call this 1 over sine x, or if we feel like it, we could call it cosecant x. Okay, the next thing we're going to do is prove some identities. And we're only going to do a couple here, but there'll be more in the assignment. So there are some ideas for what you can do. You can bring everything to sine and cosine if that looks like it's going to be helpful. If you see an opportunity to use Pythagorean or double angle identities, use those. The algebraic operations you can consider are factoring, especially for reducing fractions. Use common denominators for add, subtract fractions. Multiply by 1, often with conjugates. So conjugates are pairs of binomials like this. If one is a plus b, the other one is a minus b. Sometimes we want to split fractions if we want to make multiple fractions, and expanding expressions, so things like squaring or cubing a binomial. So when we say prove, we can't assume that these things are true. We want to show that they're true. So instead of having the equal sign, we're going to have sort of a wall between them. And I'm going to try and turn the more complicated side into the simpler side. Okay, so I have 1 over 1 plus cos x plus 1 over 1 minus cos x. So right away, I'm thinking, wow, that's two different fractions. The right-hand side only has one expression. I probably need to put those fractions together. And if I do that, I need a common denominator. That means multiplying the first one by 1 minus cos x over 1 minus cos x, and the second one by 1 plus cos x. Okay. The reason we can do that stuff in green is because that's really just the number 1 that I'm multiplying by. So let's see what that gives us. 1 minus cos x on top from the first one, 1 plus cos x on top from the second one, and the whole denominator is 1 minus cos squared x. If I multiply out those brackets, I'll have 1 minus cos x plus cos x minus cos squared. Okay. Put them together on top. 1 minus cos x plus 1 plus cos x. The cos x's are gone. The bottom, we could rewrite 1 minus cos squared x as sine squared x. And that's because of this fact. Sine squared x plus cos squared x equals 1. Rearrange it. Sine squared x is just 1 minus cos squared x. And finally, we know that a sine squared on the bottom is the same as a cosecant on top. That's the definition of cosecant. It's the reciprocal of sine. Okay, so now we've turned the left side into the right side. We can say the left side equals the right side. Therefore, the identity is true. But you need to clearly show your steps, because the real math here is in the process. We know, or we assume, that that given statement is true. Let's try another one. Sine 2x equals 2 tan x. Sine 2x, rather, over that whole thing equals 2 tan x. Okay, so right away, when you see sine 2x, you should be thinking, oh my gosh, there's a formula for that. If I go way back here, sine 2x had this whole thing. So let's put it to use. Sine 2x is going to be 2 sine x cos x. Cos 2x. There are a bunch of ways that we can approach that. There are 3 different identities that come for cos 2x. But generally, if there's a cos squared over here, we want to work in only cosines. So I would go with this identity. So I'm replacing cos 2x with this. Then I have minus cos squared x plus 1. Let's clean up the bottom. That's 2 sine x cos x all over cos squared x. Notice cos x and cos squared, those can divide out. So we have 2 sine x over cos x, and sine x over cos x is the definition of tangent. This side was 2 tan x from the original setup. So the left side equals the right side. Finally, we're going to look at solving trig equations that involve identities. So when we solve trigonometric equations, we would really like to have the same angle, the angle of x. Here we've got a cos 2x and a cos x. So this should be making us think, is there another way to express it? There are three different ways, but the way we would like to choose, if possible, involves only one trig function. So we can either have an expression that has sines and cosines in it, or we can have one that just has cosines. Just cosines sounds better to me. So cos 2x can be rewritten like this. Okay, that's this whole not the plus 1, just this. Okay. Then we'd have everything else that was in the equation. Let's simplify a little bit, so that'll give us 2 cos squared x minus cos x equals 0. Okay, we can take a common factor at this point, and we always factor when we have quadratics. And what that gives us is two little elementary equations. This is just like we did in chapter 4. Cos x equals 0, or 2 cos x minus 1 equals 0. We're only looking for the solutions in the first revolution. So cos x is going to be 0 right here at pi over 2, and right here at 3 pi over 2. The other one, so let's write that down, pi over 2 and 3 pi over 2. Cos x is equal to a half. Well, let's just sketch that. We're going to have a positive cosine value in quadrants 1 and 4. And the reference angle, where cos is a half, would be pi over 3. Let's figure out what those angles are in standard position. So we'd have pi over 3. And then think about this other one. It would be 2 pi minus pi over 3. Or 5 pi over 3. Those are all of our solutions in the first revolution. But the idea here is that we could not do this solution without using a double angle identity. All right, we'll take a look at the Chapter 6 assignment solutions next. But I think it's really of a great deal more value to you to download the Chapter 6 assignment and do it first, and then take a look at the solutions. Just watching me do them sounds A, incredibly boring, and B, probably not that productive. Okay, with that caveat, here we go. We're going to find the non-permissible values for tan x over sin x in the first revolution. So tan x is on top. So the only problems that could come out of this is where it's undefined. Okay, and tan x we know is undefined at pi over 2. We could use a table. We could use the fact that the graph has an asymptote at pi over 2, or so on. And it's got a period of pi, so it's going to recur later over here. So those are places where tan x is undefined. Tan x being 0 is no problem at all. Sin x, on the other hand, is never undefined. But where is it 0? Because having a 0 in the bottom would be bad. And we know that the sine is 0 wherever the y values on the unit circle are 0, which would be at 0 and at pi. If we put all those together, we can say that x is not allowed to be any of those. 0, right here. Pi over 2, right here. Pi. And finally, 3 pi over 2. Okay. Notice that that's only worth 3 marks out of the whole assignment. So it's not where the bulk of the material is for the chapter. Simplify tan x cosecant x into a single trigonometric ratio. So again, if we want to simplify, one of our first techniques we can use is just to convert to sine and cosine. Okay? And when we do that, we'll see that sin x over sin x divides out. we have 1 over cos x, and that is secant x. Number 3, rewrite 1 plus cotangent x over 1 plus tan x using only sine and cosine. Well, I'll just do that much first. So this would be 1 over cosine over sine all over 1 over sine over cosine. Okay, one of the common errors that we'll see here is people doing this, dividing out the ones. That is bad. Don't do that. Okay, we want to convert to a common denominator on top or on bottom, maybe use some other trick, but we can't divide out in pieces. Okay, so what we have is 1 plus here. So if I want to put the top together in a single fraction, I'll need a common denominator. So I could rewrite the number 1 as sine x over sine x. I'm just timesing it by sine x over sine x. And on the bottom, I could write the number 1 as cos x over cos x. And again, that's just so that we get a common denominator. Once we do that, the top is sine x plus cos x all over sine x. That whole thing is divided by cos x plus sine x all over cos x. We're almost done here. If I want to divide fractions, I multiply by the reciprocal of the second one, or the bottom one. So I'm flipping the bottom upside down. And now we have terms that we can divide out. And I divide them all out. That is a whole bottom divided by a whole top gives us 1 here, which is cos over sine, or as a single trig ratio, cotangent x. So look for those common denominators. All right, let's prove some identities. The right side here is cos x. Left side is sine squared plus cosine squared over secant x. So if we go through this, sine squared plus cosine squared, we know that that is 1 over secant x, okay, which would be 1 divided by 1 over cosine x, which is the same as flip and multiply. So by the time we're done, we get cos x equals cos x. Now, if you didn't show all those little steps around here, that's probably okay. We know that 1 over secant x is cos x. But you do need to show that sine squared plus cos squared becomes 1. All right, the next one. There are a whole bunch of ways, typically, for us to show a proof. So you might decide to work with the right-hand side. I'm going to choose the left-hand side. And I can see here that I've got a binomial in the bottom on the left side. And I would really like just a single term. The way that we accomplish that is by multiplying by the conjugate. So we'll get cos x minus 1. And we'll have to times the top and bottom by that. Okay, so up top, I'd get sine x by cos x minus 1. We could multiply it out. It'll turn out in this case not to be that helpful. We'll just have to factor it out again. So we could leave it like this. But if you do, there's no problem. Okay, now we've got cos squared minus 1 in the bottom. And we think about this. Sine squared x plus cos squared x equals 1. Let me build one of those cos squared x's minus 1. That would be equivalent to negative sine squared of x. So now I've got sine x, cos x minus 1, all over negative sine squared x. Here's where we can start to divide. A sine x over a negative sine squared is going to give us this. So we have cos x minus 1 over negative sine x. We're almost there. There are a whole bunch of ways that we could show how this is going to turn into what we want, the 1 minus cos x. One way would be to multiply the top and bottom by negative 1. And that will give us a positive 1, a negative cos x, and all over a positive sine x. So when we're done, we can say the left side equals the right side. Therefore, the identity is true. So if you have a binomial on the bottom, you want a monomial, use those conjugates. Okay, C, we have tan, cos, and sine. There's some fishy stuff here. First of all, maybe we want to go to sine and cosine. I think I want to turn that left side into the right side. So I'll have 2 tan, which is sine over cosine, times cos squared. Okay, you can see here, cos squared on top, cos on bottom's gone. We get 2 sine x cos x, and that is your double angle identity for sine. So from the little formula sheet, we know that that's sine 2x, left side equals the right side. All right, in this last one of our identities, we've got cos of the 4 minus sine of the 4 on top. Clearly, the right side is the simpler side, so we're going to turn the left side into the right side. On the bottom, we have a cos 2x. Now let's think about the things we might be able to do with the top. The top has a sine and a cosine. There are 3 different identities for cosine of 2x. I'd be inclined to use this one because it looks a lot like what's on top. You can't just divide these out in pieces. You can't just say cos to the 4 over cos squared is cos squared and sine to the 4 over sine squared is sine squared. What you have to do to reduce a fraction is factor. So up top, we could turn this into cos squared x plus sine squared x. And on the bottom, we had cos squared x minus sine squared x. I didn't bother factoring the bottom because I can see right here that some things are going to divide out. If you had factored the bottom and kept factoring the top, it still will work out for us. So what are we left with? We're left with cos squared plus sine squared x, which we know is 1. But it's really important that we show the steps to get there. Okay, this looks a lot like an angle sum or difference formula. We want to write it as a single expression and then evaluate. So sine 43 cos minus cos sine. Sine cos minus cos sine. It turns out that's our angle difference formula for sine. So I can rewrite this as sine 43 minus 13, which is the sine of 30 degrees, which we know is a half. Okay, so 1 mark for putting it at sine 30, 1 mark for evaluating it. Use a sum or difference formula to determine the exact value of tan 75. So how do you build a 75? We could do that by a 45 plus a 30. That's going to make our 75. And then we'll just have to go to our angle sum formula for tangent, okay, which is tan A plus tan B all over 1 plus, or rather 1 minus tan A tan B. So writing it out, we'd have tan 45 plus tan 30 all over 1 minus tan 45 tan 30. Okay. Straight from your formula sheet. I'll work this vertically here. So tan of 45 is 1. Tan of 30 is root 3 over 3. This will be 1 minus tan 45 is 1 times root 3 over 3. If I want to simplify this further, I could get a common denominator on the top, so I'd have 3 plus root 3 over 3. All over on the bottom, I'd have 3 minus root 3 over 3. Okay. If we are dividing fractions, we're flipping and multiplying, which gives us a final result of 3 plus root 3 all over 3 minus root 3. If we rationalize the denominator, we could show that that's going to become 2 plus root 3. But I'm fine with you leaving it as that non-nested fraction. Okay, we want to find the sine of 165. We're going to have to use two convenient angles. Okay, and to get to one that ends in a 5, you're definitely going to need your 45. So something plus 45. 120. Is 120 an angle we can work with? Absolutely. It's an angle with a reference of 60. So now I'll just use my sum formula for sine, which is sine A cos B plus cos A sine B. Sine 120 is root 3 over 2. Cos 45 is root 2 over 2. Cos 120, that's negative a half. And sine 45 is root 2 over 2. So by the time we're done, we get root 6 minus root 2 all over 4. The big idea here is that you need to find a way to re-express 165 in terms of the sum of angles that you know something about. So if we had written this as sine of 130 plus 35, that's useless because we don't know anything about sine 130 or 35. It's only our basic angles, 0, 30, 45, 60, 90, and their multiples. All right, so same idea here. We've got a sine that's a sum. So when we have sum with a sine, it's sine cos. Again, this is just straight from the formula. Cos sine. Right. The sine or the cosine of pi is negative 1. You could even throw it in your calculator. The sine of pi is 0. By the time we're done, we get negative sine x. Number 9, we want to turn this into a single trig ratio. Well, this looks really fishy. It's got a sine and a cos multiplied together. And I know this thing. 2 sine x cos x equals sine 2x. Let's see if we can use that in here. I would really like to see a 2 sine 13 cos 13. Now this whole thing was 8 sine 13 cos 13. So really we've got 4 times 2 sine 13 cos 13. So what do we get? We get 4 times the sine of 2 by 13, or 4 sine 26. Okay, there are a whole bunch of ways to approach a question where if you know sine, then you want to find cosine. And if you have a way other than the way I'm about to do, that's fine, by all means. As long as it gives you an appropriate answer, you're all good. Okay, we know that this angle's in quadrant 3. I know sine, I want to find cosine. Here's the identity that I'd be inclined to use. Because all it has in it is sine and cosine. Sine theta is negative 12 over 13. Cos theta is unknown. So I get 144 over 169 plus cos squared equals 1. Move over. This is 25 over 169. We're going to want a square root. So the square root of 25 over 169 is 5 over 13. And when we square root an equation, it could be either positive or negative. So that's all the algebra that's involved. So we just subbed in a number and then we moved it over and square rooted. Now we need to do a little thinking. We're in quadrant 3. So is cosine theta going to be positive or negative? It's going to be negative. If we want to find the cos of 2 theta, well, we have 3 choices. We have either this formula, we have this formula, or we have this one. Now, I'd argue in this situation that the smartest one to use would be the last one, because you have no doubt what the sine of theta is. Even if you botched part A, you can still get part B here. So we can have 1 minus 2 over negative 12 over 13 squared. That's 1 minus 2 times 144 over 169. I'm going to need a common denominator. And by the time we're done, we've got negative 119 over 169. We'll do one last question involving an equation. So right here we've got sine 2x and sine x. Right away we know we're not happy that we have 2 different angles. But we've seen this before. Sine 2x, we can rewrite it. We can rewrite it as 2 sine x cos x minus sine x equals 0. There's that equation rewritten with a trig identity. And once we do that, we're often looking for ways to factor. The simplest way to factor, and the way you always look for first, is a common factor. So if I take sine out of that, I'm left with 2 cos x minus 1. Each of these gives an elementary equation. So sine x could equal 0, or 2 cos x minus 1 could equal 0, which means that cos x equals a half. Okay, let's solve each of these. We're only asked to do it for the first revolution. So sine x is 0 at 0 and at pi. And you can check that out either from the chapter 4 material or think of it as the y values on the unit circle. So we have solutions of 0 and pi. Cos x is a half at a reference angle of pi over 3. Cosine is positive in quadrants 1 and quadrant 4. So that gives us solutions of x equals pi over 3. And this last one would be 2 pi minus that pi over 3, or 5 pi over 3. There are all our solutions in the first revolution. Out of the material on this video, the most important stuff would be being able to manipulate trigonometric expressions, being able to prove some identities, and being able to work with your sum and difference formulas. I hope you found this helpful. Once again, there are downloadable notes in the description below, and there's a blank copy of the assignment as well. Take care.